We found a set of equations for several fundamental variables in stellar interiors, yet they all depend on the density, and we do not yet have an equation for the density. This is because the density follows the equation of state, relating pressure, density, and temperature. So that when two of these quantities are specified, the third one is assumed. Yet, there is a useful equation that allows us to identify some properties of stellar interiors, which is the Lane-Emden equation. Let's find out how we get to this equation. So let's get first the equation of hydrostatic equilibrium. You have that it is dp over dr is equal to minus gm r over r squared times the density. If you take the derivative of this, you're going to have on the right-hand side the derivative of the mass, which is the mass continuity equation. Remember, the mass continuity equation, dr, dmr dr is equal to 4 pi r squared times the density. So let's take the derivative on both sides here of the pressure equation. Now, if we substitute this by the mass continuity equation, then this becomes minus g 4 pi r squared rho. Now, divide both sides by r squared. Now, the right-hand side is the same right-hand side of the Poisson equation for the gravitational potential, which in spherical coordinates is... So if we compare these equations, we immediately identify the gravitational potential with the pressure gradient, as expected from a situation of hydrostatic balance. If we now use the following ansatz for the equation of state, then plugging it into the equation yields... Now, if you had gamma equal 2, then you would have a perfect Laplacian. Well, this is not always the case, but we can use a mathematical trick to zero the exponent on the density inside the first derivative. We can replace the density with a constant, say the pressure at the center, and a function theta to the power of n. So rho c here is the central density, and theta of rho is a dimensionless function that is carrying the radial dependency of the density. So the density derivative then becomes, and if you substitute that back into the original equation, then you have... Now, to have a Laplacian in the left-hand side, then we need to cancel the exponent of theta. That is, you need to have a relation between gamma and n, so that gamma is equal to n plus 1 over n. If this holds, then the equation becomes... Now, the constants on the left-hand side have dimension of distance squared. So that means that we can define a length where lambda has dimension of length, and c is dimensionless. Now, replacing radius by lambda epsilon, we finally find the Lane-Emden equation. Solving for theta, then we have the density because of this relation. Now, notice lastly that because we defined gamma as n plus 1 over n, then the pressure is then given by kappa times the density to the power of n plus 1 over n. And this is known as the polytropic equation of state. The sun is very well approximated by a polytrope of n equal 3. Low mass stars are approximated by polytropes of n equal 3/2. Giant planets are well approximated by polytropes of n equal 1. Now, the Lane-Emden equation has analytical solutions only for 3 integer values of n. These are for n equals 0, n equal 1, and n equal 5. You have here some of the solutions. N equals 0 is the black, n equal 1 is the red, n equal 5 is the violet. The other ones are numerical solutions. N equal 2 is the yellow, n equal 3 is the green, and n equal 4 is the blue. Now, essentially, the Lane-Emden equation works as an equation of state. In the absence of the Lane-Emden equation, the density has to be derived from the pressure, temperature, via the ideal gas law, as one solves the equations of stellar structure. Here is the solution of the Lane-Emden equation for n equal 3. We get the density in the interior of the Sun.